So welcome to our final review. You guys hopefully have your review packet out. If not, you can just try to follow along by pausing it when I give you some time to answer the questions ahead of time. So this is going to be our key. I have, of course, my many colorful writing utensils here. So, key. Yeah. Let's get started. So if you guys think back, quite long ago, you should remember that charge has units. It starts with a C, so coulombs. Watts is power, neutrons is force, electrons is it's not a unit, it's a thing, it's quantity. Not a quantity, but physical existing thing. If a particle at rest is in a magnetic field of 2 teslas, what magnetic force does the particle experience? This sounds like a very crazy question. You have to write down a formula, but you'll see that if a particle isn't moving, it's at rest, which quantum mechanics, not a thing. But if it's at rest, there's no force, because force is equal to Q V B. No velocity, no force. Magnetic domains for permanent magnets. We looked at that. We watched a video on it. It was fun, hopefully. You should know that they have to be aligned. So that's not aligned. That's chaotic. That looks like everything's going the same. That's alignment right there. Cool. Everything's aligned, achieve the same goal. Sweet. Now we keep going. Excuse me, got a little bit of cold. Which of the following symbols is the schematic symbol of a resistor? Now, that's a diode. That is a battery. It's that. Yeah, it's totally squiggly, angry line. We remember that, hopefully, from circuits. I know some of you are going to be sad, but we don't have to build a circuit on the final exam. We're just doing math. Yeah. Oh, well. In a parallel circuit, which of these equations describes it? Well, if we're looking at these equations, we're going to parallel. Now, it's going to be this one, by the way. Let's see. That's series. Nope. Yes. Cool. Done. There's the first page. Take a gander at its gloriousness there. See if I can get all the answers in one shot here. Yeah, sure. There you go. All the answers for the first page in one shot. Go. Okay, let's move on. Next page, we got some questions. Now, if you were there in class, you heard number 6. That's kinematics. That's not what we were covering this semester. But just for fun, we'll go ahead and solve it. So you have an object starting at rest, dropped, reaches the final velocity. You want to know the final velocity. So you want to solve for VF. If you look for your kinematics equations, you don't have time. The only equation without time is equation 4. So you're going to use equation 4. Vf squared is equal to V0 squared plus 2AD, which is displacement, but we'll worry about that when it comes up. So if you stare at this, the initial speed was rest, so this is 0. 2 was 2. A on Earth is -10, and D is displacement, actually. It's a vector. It has direction. It's going down 5 meters. So this is -5. So, cool. It's plus or minus, and you guys know you want the minus because it's going down, right? It's going down towards the Earth. So it's going down towards the Earth. You want the negative side of that, and, yeah. So you're going to get 10 times 10, which is 100. 100 square rooted is 10-ish. If it's going to round to 10 if you use 9.81. There you go. 10's closest. Energy, is it a vector or scalar? It is also it's conserved. So this is both A and D. That's totally magic of Google Docs being converted to Word doc, or maybe I backspaced one too many times when I was deleting classical mechanic problems from an older final. Power. Those units of Watts, not joules, because that's energy, not newtons, because that's force, and not distance divided by time, because that's not units. That's an equation. Which of the following? Oh, not sorry. What is electric force between a proton and a neutron? So this is that great trick question. You might be like, well, we need the equation. F is equal to K Q1 Q2 over R squared. And then you're going to be like, wait, neutron. Has no charge. Zero. Because 0 times anything is 0, so it's going to be 0. The equation matters, but like neutrons don't have a charge, that there's no electrical force. That's also this kind of concept. Logically makes sense. Electric force is often, now this is probably not going to show up on the test, but it's certainly greater. I don't care what people say. It's absurdly greater than the force of gravity for particles. It just is. And nuclear force is even stronger, depending on the particle. Some things don't actually like experience it. But I mean, if you're doing it, it's fine. Semantics. Anyways, you got, this looks like optics, right? Oh, you guys can't see it. It's because you need color. No. But this looks like geometric optics. So this is going to be Snell's law, right? N1 sine of theta 1 is equal to N2 sine of theta 2. You guys want to solve for, you're staring at this, you have the incident angle, so you want the refracted angle. Refracted angle is theta 2, so you're going to get N1. Wow, it died. Tragic. Christmas colors all the way. N1 divided by N2. Sine of theta 1, and theta 1 is 30. And that's equal to sine of theta 2. If you do the math trick of a lifetime, you want to get rid of this sign. You have to do the anti-sine function. Anti-sine function is also called inverse sine or arc sine, depending on when and where you were in life. But so if you do inverse sine of both sides, you're going to get the inverse sine of N1 over N2 sine of 30, which you guys know is 1/2, but we'll leave it like this for now. Next, you want to start plugging in other things. You know, N1 is air, which is 1. You know, N2 is glass, which is 1.5 in this case, so it's 1 divided by 1.5 times 0.5. And now, of course, as we all know from this, we're going to go ahead and Taylor series expand sine of theta into its, of course, series of theta minus theta cubed over 3 factorial plus theta to the 5th over 5 factorial. And we'll go ahead and truncate it here. And the first two terms, I'm joking. We're not doing that. We're using a calculator. We're using a calculator, guys. We're not. I know I like to give the engineers like flashbacks and like torture, and they're sad, but we're not going to do that. Okay. And we're back. So we're back. So we did the inverse sine of 1 divided by 1.5 is 0.5. 19.4. So if you're doing sig figs, we have 1 sig fig. So technically it should be 20, but we'll go with 19. We'll go with 2. Cool. So there is all these problems done. Let's try to get all of these in one shot. I can't get all of these in one shot, can I? There you go. That's kind of all of them. That's because I can get with this camera. We're moving on. Ooh, now we're to show your work problems. Guys, look. Number 1 came back again. It's number 1 again. We're just starting with the first problem again. So here's the first problem. Yeah. So to go over this, let's pick this marker. We'll switch if we need. So first step on problems like this, when you're actually reaching the actual show your work problems on a test, is to figure out what unit they're from. So you can't figure out what unit they're from. You can't. What equation are you going to use? It's very useful to figure out what unit they are from. So this one's clearly magnetic. Magnetism, right? It's going to be magnetism because there's nothing about electricity in here. It's not electromagnetism, though it could be. In fact, it becomes electromagnetism probably down there. So, starting in magnetism world, though, just straight magnetism. So a wire in the X plus direction has a current of 10 amps. If this wire experiences a nearby magnetic force of that in the Z direction, what is the magnetic field 100 meters away, and what is the direction of said magnetic field? So you want to solve for B, as you all remember. Yeah. So what equation would you want? Well, we got a current. We got a force. We got a distance. So we know that force is equal to Q, V, B. We're going to ignore the cross product because we're going to use the right-hand rule because everything's in, 90 degrees of each other. So let's change it though, right? You can change this equation. So if you remember that this is equal to Q, distance divided by time, B. You know that time is can be moved, so now you can get Q divided by T, dB, and this becomes Q divided by time. Charge divided by time is current by definition. So this becomes force is equal to current, distance, magnetic field. So at this point, we got a current, we got a force, we got a distance. We can solve for magnetic field. So let's start plugging in what we got rather. Force is 2 times 10 to the negative 2. And that's equal to Q. Well, we're not using Q, we're using I. I is 10. Distance is 100. And magnetic field is what we are solving for. So, luckily, because I like making problems, I guess, these are nice numbers because they're powers of 10. So you're just moving decimals, or in this case, changing powers. So let's change the power sum. So we're changing power, decreasing, we're going to divide by 10. So this is going to decrease by 10, so this becomes 3. Then we're going to divide by 100. If you divide by 100, you're decreasing it by 1, 2 zeros. So 3, 4, 5 becomes 10 to the negative 5. 2 times 10 to the negative 5. So the magnetic field, let's move right over here. I guess I've been running out of room. I should really give more room for this. Oh well. Sorry about that, I was interrupted, but now back to it. B is equal to 2 times 10 to the negative 5th. Then you got to remember for the units of magnetic field, it is Teslas. Finally, you got to figure out the direction. So you're using right-hand rule. Yeah, the grid, right? So we're using the grid. Your thumb goes in the direction of force. The index finger goes in the direction of current / charge, or sorry, current or the speed the charge is going with. And this middle finger is magnetic field. So force goes into the Z direction, positive. So force is thumb, it's pointing inward. No, outward or towards you, towards me rather. Inward would be negative. Outward with positive, cool. Which might change depending on who your professor is. X goes into the positive X direction, which is that way. So our magnetic field, which is going this way, or up, is in the positive Y direction. So Y plus, which I'm just leave as Y. So here's our answer after all that math madness. Ooh, kind of cutting off the 5. but it's 2 times 10 to the negative 5 Teslas in the y direction. There's our vector form. It looks beautiful. Beautiful. Next, sketch this wire and the magnetic field. So it's a wire. Yo. So we got a wire. It's shown here. You got a current. Now, surprisingly to most all of us, because of how we only used the right-hand rule. And the math and equations giving us this, because you know it's going to go in a loop around that wire, right? But the way we solved it right now, at this moment, it is going in the positive y direction. This would be our magnetic field. That would be the current. Which makes sense because it starts, when you're wrapping your finger around the wire, it starts by going this way, and then slowly as it goes around the wire, right? It's going up originally. Initially, it's going straight up. So that's using it as the right-hand rule, not the shortcut one with the thumb, but we all know it's going to create the loops. Last one, what would be the electric field experienced by this wire over 2 seconds? Now this is key to calculating that. And that will give us everyone's favorite thing ever. We're going back in time to, well, maybe not back in time. I guess it's still back in time. To the wonderful Lorentz law. So the Lorentz law. So for Lorentz law, we have force is equal to Fe plus Fb. We have over 2 seconds. That's good. That might help us. We'll find out. So in this case, so I did make a mistake. That cough was not just because of minor cold-on fighting, but yeah, that's wrong. So you're going to see that part of the video, because I'm going to cut it out with the right part. We're not using the Lorentz law. Well, I mean, we kind of are. But the electric field, right? Electric field is going to be equal to what electric field would be experienced. Well, we might actually use the electric. No, we're going to do it that way. So this is K Q over R squared. There's one equation of it. Let's see. Electric field of this is experienced over 2 seconds. So we can get charge, right? This charge would be I is equal to Q over T. We know that we have 2 seconds now, though. So Q is equal to I times T. We have I. I is 2 amps. Yeah, I is 2 amps. So Q is 2 times 2, which is 4 coulombs. So we know the charge is 4 coulombs. So can we get a distance? Experience it over this wire over 2 seconds. Well, I can feel 100 meters away. So we're going to use 100 meters away, right? That's going to be electric field you're going to experience 100 meters away. That's kind of missing from this part of the problem, but that's fine. So electric field is K, 4. That's 4 coulombs. That's a unit. That's not speed of light. That's not speed of light C. That's unit C, coulomb. So you don't include it in math. R is 100 squared. Now we could, of course, put in K. So let's just do it this time. K is 9 times 10 to the 9th, roughly. There's 4 divided by 100 squared. 100 squared is 10 squared. 10 squared squared is 10 to the 4th. So 4 of these murder. You get 5. So you get 9 times 3. Sorry, 9 times 4, which is 36 times 10 to the 5th. Now, you guys, of course, remember the units of electric field, right? Newton coulombs. Again, this is not a great question. Technically electromagnetism, but not really. We'll probably just, this part C in particular, won't show up on your final, I promise you. It won't show up on your test, I promise you. It's not good. Not good. Poorly defined. Still ranting about it. This was wrong. That was stupid. This is right. Okay. Fixed it. Cool. Moving back. Next. Hey, we went from number 1 to number 20. No. There was another one. 26. Even better. Just, as you guys know, the numbers make perfect sense. Just don't think about it too much. So, we got circuits. I'm going to pick orange because that's a good color for circuits. So for this circuit, solve for the total current and resistance. Doesn't say power, does it? Nope. Both the total current and resistance. So we're going to get total current and resistance for this circuit. You know, I know you guys like building them, but sadly, we're doing math. So you guys remember how to do this, right? You want to start somewhere. This seems like a good spot to start. This is a junction, because these two are different than those two. So these are what you would often call parallel. Exactly. So everyone knows this dies. This becomes the only one left, of course. And this one's value becomes 1 over 20 plus 1 over 20 to the inverse 1. If you do the math for this, you'll get, I'll call this 1. We'll call this 1. You'll get this as 10. It halves, you remember the shortcut rule because they have the same value, but you don't need to know that. But yeah, so this is now 10. It's not 20, it is 10. So that's the first junction. Let's go to the second junction. We're going through all of this. You could do this, or you could do this, or you could do this. I'll do this because this one looks nice. This will be the one I call the second junction. Okay, so we got 3 values, 30, 50, and 20. These, if you follow through, are a straight, continuous line of current. So it's series, you're adding them. So 30 plus 20 plus 50 is 100. So these merge into one resistor. That is 100 ohms. So these are now all dead. So our series 2 is equal to 30 plus 20 plus 50 to get that 100. That's where that 100 comes from. Cool. So now we're done with 2 blocks. Let's keep going. Let's go ahead and go back to the fun one. That's this one. So these are parallel, but these are series, right? These two are series, but they're parallel combined to this. So I like to do this way. We got parallel right, not parallel, sorry. We got series right there, and then we'll do a parallel of whatever these merge into. So this would be 10 plus 10, which is 20. So they merge into one resistor. Neither of them exist by themselves. It's not 10. It's not 10. It's now 20 ohms. This one is 3, and 3 is given by a series equation of 10 plus 10. Now we keep going, so that's where the 20 comes from. These both now, this is parallel. So they were parallel before. They're still parallel, just it's easier now. So this is 1 over 10 plus 1 over 20, because these two merged. And this is 4, right? Yep, 4. So at this point, you're going to have to get out some calculator or do some tricky math. So try the tricky math first. So this would be 2 over 20, and that would be 3 over 20. Then you'd flip it, so it would be 20 over 3, which most people do not like. Again, we got that because we need a common denominator, so these both have to reach common denominator. The only way to do that is multiply this by 2 over 2. We're multiplying by 1 by that, right? So this becomes 2 over 20 plus 1 over 20, which is 3 over 20. 3 over 20 flipped is 20 over 3. Now that, not a good number for most people, so let's get out a calculator. 20 divided by 3 is often 6.6 repeating, which we can round whenever we want, but I'll leave it as 6.6 for now. This becomes 6.6 ohms. So now we go back here. These all merged. So this is now dead. And this all merged into one resistor that is now equal to 6.6 ohms. So we got 6.6, that's series to this, which is 100. This isn't series though, this is series. So we have to deal with this, and then it's series, 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 and series. But we gotta get this series first. So I'll try to use my green, although it's dying. Hope for the best. Oh, it's working for now, that's good. So this is number 5. So this is a parallel. So resistance 5 is equal to 1 over 100 plus 1 over 100. Flipped, which is 2 over 100, which is 100 over 2, which is often 50, unless you do the math wrong, which happens a lot. So if you do the math wrong, you won't get 50. That's how that works. So these both merge. So this is now dead. We're going to have them both merge right here. So it's in that straight line. And this is no longer 100, it's 50. So now, trying to show this best I can. Let's use last one. You got a path, right? Path goes like this. We go from here. Then we go through here, right? Because this is 50. Then this no longer exists over here. So this is 6.6. This is 100. This doesn't exist anymore. Back. So now it's continuous loop. These are all series. So with series values, we got 50, we got 50, we got 6.6, and we got 100. So you're going to add 50 plus 100 plus 6.6, and we'll get the total resistance of, again, 50 plus 100 plus 6.6. So that's 206.6. So that's 206.6, repeating infinitely. That's our resistance. Check. Now you want current, because we have resistance. Good, cool, it's done. Wasn't the worst thing in the world. Now we want current. Current is V equals IR, so it's V divided by R. In this case, our V is 120. Our R is still 206 repeating. 6.6 repeating. Get our calculator. Put this in. 120 divided by 206.7. Let's round it there for arbitrary reasons. So again, if you want to use sig figs though, the number of sig figs we're limited to in this problem is 1. So technically it'd be 120, not even 120, it'd be 100 divided by 200, but I don't think that satisfies most people, so we'll do 207. We'll just do this. That's probably what most people would be fine with. Oops. So quit. That works. 207. We're around 206.6 to 207. So the current going through this is 0.58. 0.58 amps. Amperes. And there's our answer. We got both current and resistance done. That was 26. Hopefully it makes sense. Hopefully it's not too bad. Hopefully it's good review. Now on your test, you'll probably have to solve for power. So let's just add that real fast for fun. By fun, I mean, you know, probably not fun, but good to know. It's good to know. Power is current times voltage. Well, we got the current, it's 0.58, and we got the voltage of 120, so 120 times 0.58. We'll get that number, 69.5. So I'm going to round it to 70 watts. It's a lot of watts, by the way. But yeah, there you go. That's all of that. That's hopefully not too bad. Now we move on to everyone's favorite thing ever, more math problems. It's 27. Hey, we're kind of going in order now, right? 26, 27. Yeah, we're kind of doing order. Oh, by the way, I forgot to mention, before we started this is clearly a circuit. Even says circuit. So it's from circuits, the unit. Yeah, okay, anyways. So next problem, we got an evil laser and an evil Bob, who's So evil Bob is the opposite of an accountant. So what's an evil accountant? That's a tough one. I guess it'd just be like, I don't know. But evil Bob has a laser. Bob wants to study it. This is clearly going to be optics because laser. Also, there's angles. And there's angle incident. That's all optics words. So it's optics. First thing we're going to do is sketch a picture. This is going to be the greatest challenge for everyone involved. So let's draw a picture. So we got a line. This is our medium separator. So the laser comes in. Our laser is going to be blue. Who knows what color it actually will be, but it's blue for this problem. The laser travels through plastic. What speed it travels through plastic? So the laser hits plastic with an angle of incidence of 40 degrees and then leaves this material with an angle of incidence of... Okay, so like we said, we changed this. So this is not... hits plastic, angle incidence. So it's coming from air. So it's coming from air and leaving the plastic. This should be travels. That's what we changed. Travels and travels through this material. Yeah. There we go. So this should be travels through, not leaves this. So this travels through this material. So it's coming from air into the plastic, traveling through the plastic. So let's draw it. So it's coming from air. Angle incidence of 15 degrees. So angle incidence of 40 degrees. So we're going to draw our dotted line, try to get 40 degrees right, which I will not do probably. There you go. It then goes and refracts towards 15 degrees. So much less, much tighter. So there is my picture. This is 40 degrees. This is 15 degrees totally. You can't even see that on the camera, but I promise you that's a 15. Just really hard. Yeah. You can also write down the mediums. This is N1, which is 1, because it's air. This is N2, which we'll figure out, won't we? Assuming this laser came from air, calculate index of refraction of plastic. Yep. We're figuring it out. Shocked. Let's stick with blue. It's a nice color for this. So we're going to use Snell's law clearly. We've got two N's. So N1 sine of theta 1 is equal to N2 sine of theta 2. And now we're solving for theta 2, right? No, sorry, not theta 2. N2. So we're going to plug in some numbers. So N1 is 1 sine of 40 divided by sine of 15. And that will be equal to N2. Now, 1 times sine of 40 is 40, so we're going to grab our calculator. Make sure it's in degrees, by the way. I didn't say that for the first one of these we did. Make sure calculator's in degrees for this always. We do sine of 40 divided by sine of 15. And you're going to get 2.48. You guys can see the mic reflecting off this calculator. Just ignore. Wait, actually, is that the camera? That's the camera. 2.48 or 2.5 in my case. So I am lazy. So this becomes N2 is equal to 2.5. What speed does it travel through the plastic with? Okay. That sounds like a good time to use your favorite equation ever. V is equal to... Wait, I did it backwards. We should start with actual is. N is equal to C V over C, right? Can I remember this? Does that make sense? No, it's C over V. I'm right. That was right the first time. C over V. So we're going to solve for V. So in this case, V is equal to C over N. So we're going to take the speed of light divided by N. So speed of light, don't forget this is wave speed. Speed of light is 3 times 10 to the 8th when we use the approximation, which we always use in this class, divided by 2.5. You'll get that all full numbers. That's 1, 2, 3, 4, 5, 6, 7, 8 zeros. So that's 1.2 times 10 to the 8th meters per second. Now you want to know critical angle. If you guys remember that, that's not too bad to solve. If you don't, but you also probably have an equation sheet, let's be honest. So critical angle is critical, but it's equal to the inverse sine of N2 over N1. If we're leaving this material, so leaving this material, N2 in this case is air, right? Because if it's leaving the material, it travels through the material, it's dealing with the 2.5. So that makes it N1. It's leaving then, because it says leaving, so that would be N2 would, in this case, would be 1 divided by 2.5. You're doing the inverse sine of that answer, which is 23.5, 23.6. 24 degrees if you want to be as lazy as I'm going to be, so 24 degrees. Did I switch back to blue? I switched colors. No. Oh, well. There you go. That's not too bad. There's all of that question done. So this is geometric optics question. We had a circuit question so far. We had geometric optics question. We had a terrible magnetism question. Although it started out fine. Next. Hey, magnetism. It came back. One moment. Hey, another magnetism question. We got amps, 0 actually. Sketch the magnetic field. This time we're using the right-hand rule the right way. So put the thumb, wrap it around if there's current. No current, no magnetic field. This one has a magnetic field. It can go like this, around the wire. It goes like this, where my thumb is the wire. Not really, but this is the wire. It's wrapping around this way. Not this way, but this way. But yeah, so here's the magnetic field. And hey, there's a B. That was part A, this is part B. A magnetic field intersects a surface that has an area of 2 meters squared. Hey, it was nice on that one. At a 45-degree angle. And the magnetic field has a strength of 8 Tesla. What is the magnetic flux through the surface? Hey, magnetic flux showed back up. You guys remember that equation, right? This magnetic flux is equal to BA cosine of theta. So magnetic field in this case is 8 Tesla. The area is 2. And now we're to the trick, where it's cosine of theta. But you know, it's cosine of 90 minus the given angle, because you want to find the angle from the surface normal, which for flat surfaces would be 90 minus the, given angle, which it's 45, so that's a coincidence, by the way. It won't always be as nice as that, but it is this time. Or maybe, won't be always as lucky as that. Don't expect that on the test. It's probably like 30 degrees on the test or something, in which case you'll get 60. This will be 90 minus 30, which is 60. But yeah, 8 times 2 times cosine of 45. 11.3. 11.3. Then you guys remember the units, right? That's right. None of us remember the units, but it's Teslas times meters squared. Now, if you did remember the units, good job. Proud of you. So next. Oh yeah, this doesn't have a magnetic field. Next. So that was another magnetism question, particularly over magnetic flux. Anyway, next. I like to rant. You guys know how I am. Matter has a wavelength. So let's calculate it and see what can deflect that. Anyways, matter has a wavelength. So let's calculate it and see what can diffract around a pion. What is the wavelength of a lazy neutron that is traveling at a speed of light? Okay, that's not lazy. Okay, but anyways, speed of light through a vacuum. So neutron has a mass. That's cool. Do we remember the equation? First off, what equation is this? You guys should know that this is The de Broglie equation, right? I'm saying that wrong. He's French. But, yeah. The de Broglie equation, as you guys, of course, know. I totally didn't forget and just Google it. I definitely forgot it. I forgot it, guys. I'm sorry. It's lambda is equal to h over mass times velocity. Technically, I didn't forget it. I knew it. I just was uncertain. So with that, let's plug in the numbers. So h, you guys know, is 6.6. I never forget this one. 6.63 times 10 to the negative 34. Mass of a neutron, the same as the proton, which is 1.67 times 10 to the negative 27. And the speed it's traveling is 3 times 10 to the 8th. Very fast. So now, of course, you know what I'm going to do before I even plug into a calculator. Let's murder some powers away. So that's adding. It's dividing so this becomes a positive value. It's dividing so this becomes negative. Also, before we can do it, we can cancel out 8 of these. Cancel out 8 of these, it goes to 19. This becomes positive. You're dividing the powers anyways. So it's going to be 10 to the positive 19 times 10 to the negative 13. So this cancels out 19 of this. So that becomes 20. That becomes, 15? So there's our powers. That's nice. So this is dead. This is dead. So now we have 3 times 1.67 on the bottom, and we have 6.63 times 10 to the negative 15 on top. That makes that way easier to calculate, I promise. People don't believe me, but I promise. Don't forget parentheses. This is the biggest mistake a lot of people make. Quite often, by the way. So if you do that, you're going to get 1.32 times 10 to the negative 15th. So lambda is equal to 1.3. I'm going to round it 3 times. Well, I guess that has 2 sig figs. That has 2 sig figs. 2 times 10 to the negative 15th meters. Cool. There's our first answer. Second question asked if an average person, what is the average person's wavelength while they are walking? Assume the average person has a mass of 90 kilograms and walks 1.4 meters per second. That's a much more brutal question to calculate, but so their wavelength is equal to 6.63 times 10 to the negative 34 divided by 90 times 1.4. Figure this is madness. Anyways, so this 0 dies and goes up and cancels. Yeah, it goes up here. This becomes 10 to the negative 35. Power rules. So you're really getting 6.63 times 10 to the negative 35 divided by 9 times 1.4. So I'm going to do 6.63 divided by 9 times 1.4. So that's 0.52. So I'm going to move this decimal once, which means we have one more negative power to add to this negative. So this is going to become in reality. I'm doing this because if you have a not powerful calculator, you have to do this because your powers will overflow. If you can put this in a calculator, great, do it. But some people's calculators can't actually handle a number this tiny. But this is 5.2, so we just moved the decimal once, right? 5.2. Now we have to add this negative up here, so this is negative 35, so now it's negative 36 in our answer. Even tinier. So much more tiny. It's kind of crazy. So do either of these above things diffract around a python. Python. Pion. Pions have a theoretical size of this. In order to diffract around it, you need a bigger wavelength. So that wavelength's smaller, clearly. It's like billions upon billions of times smaller. This is actually also smaller, because if you ignore the 10 to the 15th, because they both have it, 1.32 is smaller than 2. Yeah. So, no. Neither of them diffract. Sadness. Sadness abound. So there's that problem. That's before I kind of messed up. I'm sorry. I just keep solving these. This is quantum mechanics, clearly. You should be, before, I have to edit some of these sometimes. Before you even start, you should ask what unit is this from. Clearly quantum mechanics, because you're dealing with subatomic particles like a pion, a neutron. It could also be maybe electricity. But once you start seeing calculate wavelength or some quantum thing, it's going to become quantum mechanics. Okay, we have this looks familiar. This looks like our most let's see what we got. We got special relativity, nuclear decay, and 2 more problems after that. I think we'll go over this in nuclear decay and then call it quits for tonight. And Monday, during that lecture, we'll go over the other 2 problems, and we'll add another problem or 2 that are good test questions. And also address any questions you might have. So we've done a lot, right? 1 problem, 2 problem, 3 problem, 4 problem, 5 problems, 6 problems. So I count multiple choices as 1. But yeah, let's do this. We have a maglev train traveling near the speed of light. Don't know how people survive the journey to that, but yeah. It has a length of 20 meters. It's traveling towards a garage with a depth of 18 meters. Cool, it's traveling at that speed. How long will this train look to a stationary observer? Now, these questions are all going to be about your frame of reference. Make sure you're thinking about who is observing the thing, because that will affect your answers. So for part A, which I'm going to have green, how long will the train look to a stationary observer? If they're stationary and they're observing it, they're not moving. The train's moving, though, and it's moving very fast. So it's going to look length contracted. So you're going to use L is equal to L0. By the way, this is special relativity. I should have said that. This video is going to be very interesting. But yeah, L is equal to L0. I got an email apparently. Anyways, L is equal to L0. The square root of 1 minus V squared divided by C squared. So at this point, you're solving for not the original length, but the contracted length, so L. So in this case, L is equal to 20, because that's the length of the maglev train. Very small train, by the way, times the square root of 1 minus V squared over C squared. V squared is 0.9 C squared over C squared. Now, as we learned in class, this squared distributes, so this is actually 0.9 squared and C squared. So these C squareds will cancel when you do the math, leaving you with just 0.9 squared. At this point, it's not that bad of a problem. It's just 1 minus 0.9 squared. These problems are easy when they're in terms of C, but a little bit harder if not. You're square rooting that, and then you're multiplying 20 by that. So you're going to get a length contraction down to 8.7 meters. It's contracted quite a lot. So that is part A. Check. Part B. How long will the garage look to a stationary observer? Now this is why, again, You have to read the question carefully. I'm going to use this darker red, which looks like green maybe for colorblind, or if the camera just sucks, which it kind of does. But garage. What does the garage look to a stationary observer in the garage? Well, first off, I don't know how they're going to see what size it is from inside. Maybe they can do it. Probably fine. But you can't really see it, because the walls could be drywall. It doesn't matter. Regardless, it's not moving. The garage isn't moving. They're not moving. There's no length contraction. It's just what it is originally. So in this case, the garage length is what it is, which is the original garage length of 18 meters. I'm writing length original garage. That's the answer. Log. The log is 18 meters. Because, yeah. Hopefully that makes sense. Next, let's use blue. C. So, wait. Let's keep the checklist going. This is special relativity. We need to be sure we're not, missing anything. Checking our... Anyway, C. How long will the garage look to you as you move in? Well, who is you in this case? Imagine you are Bob, the accountant, on a maglev train. So you are Bob in this case, who's riding a maglev train. So you have finally done it. You've ascended. You have become Bob. Most of you waited for this for so long, and you finally you've done it. Congrats, you're an accountant. Not probably what you're hoping for, but at least it pays well. How long will this garage look as you move in? So, if you are on the train, here's my train, it's beautifully drawn. You're moving towards a garage. Here's my beautifully drawn garage. This train sucks. That's my train. This pin sucks too. There we go. That's a better train for sure. That's a much better train. Not terrible train at all. There's my train going towards the garage. The garage to the person in the train will look like it contracts in length, right? It's going to look all wobbly. The garage is going to look like it shrunk because to the person on the train, the garage is moving towards the train at near the speed of light, right? 0.9 c. So in this case, you're length contracting the garage's length. So this would be LG, the length of the garage, which is going to be equal to the original length, which is 18, times the square root of, again, it's just 1 minus 0.9 squared. That did not change. So you're going to get the same thing as last time. Can I go back in time on this calculator? Probably not. I cannot. I could actually go all the way back to this, 1.1 to that. Then we could be like square root. And yeah, that. So we're taking that times the garage's length this time, which is 18, which is 7.8. The garage shrunk down to 7.8 to you on the train. So length of the garage, 7.8 meters. If you are on the train, that's what it looks like. Last question is always the fun question. We got that. I'm going to write it in pink anyways. How will the train look as you move in? So you are on the train. So to you who is on the train looks like itself. So it's the original length of 20 meters. Because your train doesn't look like it shrunk to you. Because to you, you're not moving. To Bob, who is you. You're not moving. So there you go. That's the Bob question. That was special relativity. We got special relativity. We got quantum. We got magnetism. We got optics. We got circuits. We got magnetism round 2, electric boogaloo. And we got some multiple gas. So, of course, the last question we're going to do for today is this, which you guys should know because I gave it away. It is a nuclear. This is a nuclear question. Nuclear, particularly half-life. So you got the following radioactive isotopes. You got carbon-14 and carbon-9. One is a beta plus emitter and the other one is a beta emitter. You want to calculate how long it takes for each isotope to reach 10% remaining. And you want to say which is more dangerous, which is subjective, but also not really. We know. I mean, technically it's still subjective. I mean, you could argue one's more dangerous over time, but we're going to go with the one that's imminent threat. Imminent threat is what we mean by more dangerous. Which one is dangerous right now? And it's very obviously one of them. So let's calculate this. So half-life. So you guys remember half-life is N is equal to N0 1/2 of T 1/2, where T 1/2 is the half-life, T is the time that's passed, 1/2 is 1/2, N0 is the amount you started with, N is the amount you're ending with. In this case, both of them start at 100, but both of them reach 10% remaining. So there's two ways you can take that. You take it that N divided by N0, the amount you ended with and the amount you started with will be 10% or 0.1. Or you could do it the other way, which is 100, 10% of 100 is 10. So 10 divided by 100, if you use this equation even, you're going to get 0.1. It doesn't change the answer. It's 1/10 regardless. So whether you take 10% of 100 and then divide it by 100 via the equation, or you just use a ratio like this and get this, it'll give you the same answer. You could have done this in principle if you picked random numbers, like 250, and you multiply 250 by 10%. You could have done this and then divided them. You could have got the same answer. It wouldn't have changed anything. But this is more fancy. So I use this because I'm a fancy person. Total lie. So let's get the equation before we start calculating half-life. So once you have the equation, it's not too bad. This is the equation, but let's get the equation they're both sharing, because both of them want to reach 10%. So if we arrange this and we're solving for how long, right? Yeah, how long T, N divided by N0 is equal to 1/2 T over T 1/2. Now we know we want this T to come down, so you have to do something. In our case, we're going to take the natural log of both sides. Take the natural log of something rose to a power. The power comes down in front, so this becomes T divided by T 1/2. That's rule of logs. Now we want this T by itself. So let's multiply both sides by T 1/2. If we do that, the T 1/2 cancels the T 1/2, and you're going to get T 1/2 times the ln of N over N0, and we still have that floating around, so let's get rid of that too. Divide both sides by the ln of 1/2. Now at any point you could have pulled out a calculator and started plugging in numbers, but you guys know me, I like to make you guys suffer through the truth of the math, and it gets ugly. So now we're going to do one of the last steps here. So we're going to, T is now equal to that monstrosity of T 1/2, which is the half-life of whatever thing you're doing, right? So this is a variable. It changes depending on what one of these you're going to use or what one the test is going to give you, times the ln of N over N0, which we know the ln of N over N0 is the ln of 0.1, divided by the ln of 1/2. Now, most of us, but I mean most of you, do not like just ln's floating around. So you can calculate them out of existence, right? Let's grab our calculator here. The ln of 0.1 is that number. If we divide that by the ln of 0.5, we're going to get an answer of 3.32. So this equation becomes this. T is equal to 3.3, if I round 3.32 to 3.3, times the half-life. That's the real equation, right? We're just taking the half-life times 3.3. It's not too bad. But if it's 1%, you need to know to change this stuff here and recalculate. But it's not too bad, hopefully. So with that, let's go ahead and do the actual math now. So we have two half-lives that we want. Half-life 1 is carbon-14. Carbon-14's half-life, which I'm going to write as C14, half-life, is equal to 3.3 times its half-life, which is 5,700 years. So carbon-14's half-life is times 5,700 years. That number, roughly. So I'm going to round that number to 1. Yeah, how many sig figs do we have? Let's see, that's 2, that's 3. Let's go with 2 sig figs then. 1.9 times 10 to the, again, you can always convert scientific notation with this way. If you take your calculator, turn it from float to scientific, it will give you the answer in scientific notation. You don't have to actually do it yourself. But 1, 2, 3, 4. 4. So there's 4. So times 10 to the 4th. Now, what unit do we write here? That's right. You guys remember? It's written right there. It's whatever they give you. Years. So it's around for a long time. It ain't going nowhere. Okay. And carbon-14 is, of course, the one we use for carbon dating as well. It's quite useful, right? It's around for a while. You can tell how old something roughly is by how much carbon-14 is left in it. Specifically bones, because bones have carbon-14 in them. Trace amounts, but amounts nonetheless. Right, a trace amounts over, thousands, millions of years. So, next we got time 2, which is carbon-9. So time of carbon-9. That's equal to 3.3 times 129, which sounds like a big number, but it's milliseconds. It's not staying around for all. Is that accurate? Probably not, but 425.7. So this is equal to 426 microseconds. I'm not even going to convert these to like years and years because that is obviously way smaller than that. Now you have your question, which is more dangerous? So we go by the great concept of imminent threat. Which of these is more dangerous if you're in a room with them and they are unleashed upon you? In that case, carbon-9, because it's releasing all of its radiation very quickly. Because when it decays, it's releasing radiation, right? So the amount of radiation that's hitting you is way more intense from carbon-9 than it is from carbon-14. No, over a long period of time, it's going to be carbon-14, but that's over, humans aren't living that long. So, I'm still going to say carbon-9. Carbon-9 is the one that's way more dangerous. Carbon-9, way more, let's go pure wrong English here. Most dangerous. Don't be near it. Just don't. It's also a beta plus emitter, and you guys know that's antimatter. You don't want that touching you. So yeah, there we go. That's it for today. We're gonna go ahead and do these other two problems in class. But hopefully, it was a good review so far. Gave you a good amount of confidence for the test coming up, or at least a good amount of things to study for the test coming up. Test questions will look similar to this again, but some of them will be different. Some of these might not make it onto the test. Some of these definitely will. So you see even near carbon copies occasionally, but not always. So always study, always be ready for numbers to change, and, till Monday.